In the last problem, we used the lengths of rectangles with a fixed perimeter to write an expression that represented their area. Length was the independent variable and area was the dependent variable. In this investigation, we're going to continue to write expressions using area as a context. So sometimes it's not easy to determine whether a trade is fair or not. So I want you to think about the following situation. A developer has all of the land on a mall site except for one square lot, shown here. And the measurements of the lot are 125 meters by 125 meters. So he decides, in exchange for the lot, he's going to offer the owner a lot on a different site. And in this case, one of the dimensions is going to be increased by 50 meters and the other one is going to be decreased by 50 meters. And so we want to know, is it a fair trade for him to give the other lot to the owner of the property that he wants? So I want you to think about that for a moment. It's the basis for what we're going to be talking about on our problem today. So if you've had a chance to think about that, you might think about how the areas compare. So in this case, if we look at the square, we're going to say that the area of the square is going to be 125 times 125, but the area of the rectangle is going to be 175 times 75. Okay? So if you do that calculation, you decide which one is going to be the better deal. Okay, so let's move on and check out what's going to happen in our situation today. All right, thinking about a lot, a lovely lot. Imagine it's just 3 meters by 3 meters. Let's deal with some smaller numbers here. And so in this first one, we can look at it and think about it as 9 meters squared. So what if we were to change the length of our square and increase it by 2 meters, but we were to reduce the width by 2 meters? Now the new dimensions would be 5 by 1. Therefore, our area would be 5 meters squared, which, as you can see, obviously you'd rather keep the 9 meters squared rather than the 5 meters squared. All right, so what we want to see today is that always going to be the case? Okay, so what I need you to do right now is I need you to copy and complete the table. Actually, copy down the table first, push pause here, and then we'll talk about how you are going to complete it. Hopefully at this point you have the entire table written down in your notebook. If you don't, this is your last chance. Please press pause. Okay, so we're going to take a look at an original square with a side length of 2 to begin. So we have a 2. All right, so if the square has an original side length of 2, the area is going to be side length squared, or side length times side length, so our area is going to be 4. If we were to take the new rectangle, the length is going to be increased by 2, so that becomes 4, 2 plus 2, and our width is going to be reduced by 2, so that means 2 minus 2, which becomes 0. So the new area of our rectangle is 4 times 0, which is 0. So what I want to know is what's the difference in the areas in square meters. So if we have the 4 as our original area and the 0 as our new area, the difference in areas is just going to be 4, because that's 4 minus 0. All right, I'll set you up starting on the next one, and then I'd like you to fill in the entire table. We'll discuss it more in class tomorrow, but I want you to have it all filled in when you come in. So you're going to fill this in with side lengths of 3, 4, 5, 6, and n. That's where it gets exciting. Okay, so a side length of 3 is going to have an area of 9. If we increase the side length by 2, we're going to get 5. And we decrease the width by 2, we are going to get 1. Therefore, our area is 5. Okay, hopefully you get the idea. So stop it and fill in the entire table, please. Okay, now that you have the entire table filled in, I would love for you to graph the length and the area of the original square and the length and area of the new rectangle on the same axis, okay? So you're going to do length and area, just looking at those from your table, of the original square. Pick a color. And then you're going to do length and area. You already have this table, so you don't need to make this, on the same set of axes in a different color. Okay? So your graph may look something like this. You may choose a different scale if you like, but this graph needs to be filled in with the 2 different sets of data, okay? For example, if I were to pick a reddish color for my original square, I'm going to have side length and area. So my side length is 2 and my area is 4. So I'm going to go right about there, okay? And then my side length is 3 and my area is 9. So I'm going to go something like that. Okay, you get the idea. So stop it here, finish off your graph. So now I want you to write an equation for the relationship between the side length n and the area A1, which is of the original square. So I want you to just think about it. That's what you should have filled in already in the bottom of the table. But if you weren't sure what that meant, we're just looking for basically a rule for figuring out, depending on how long one of the side lengths is, what the area would be. When you're finished with that, I would like you to write an equation for the relationship between the side length n and the new area of the rectangular lot. Once again, think about the n is the changing value, and just take a look at your table and see if you can figure that out. We're going to talk about it in class, but I wanted you to have a big head start on this so that you'd have just some questions that you needed to fill in and we could go through it rather quickly. Okay, so thinking about these 2 relationships and what you ended up with in your table, let's take a look. The original square, beautiful original square with a side length of n. So we could say that if we wanted to talk about that area, we could think about it as n times n, otherwise known as n squared. Okay, if we were talking about area 2, we know that one of the side lengths was no longer n, but it was n plus 2. And the other side length started with n, but then we subtracted 2. So your equation might look like that. If you had something different, we're going to talk about that as well. Okay, fantastic. This is a great starting point for us to get going in class tomorrow. Last thing I want to talk about, I want to talk about where we're going with tomorrow's class after we talk about 2.1. So I want you to look at the lovely square I have on the left-hand side, sort of similar to what we just talked about, except this one, it has a dimension of x instead of n. If we were just to create an extension on one of the dimensions, so x plus 3 on one of the dimensions, You see the picture to the right, okay? So I want you to think about how the areas of the original and the new one compare. So if we think about this as being x squared, and this one as being x squared, and then our additional little piece here being 3x, we could say we have x squared for the small one, and then x squared plus 3x for the larger one. Is there another way to write that? Okay, that's where we're going to go tomorrow. So I hope that has your head thinking, and we will get going on that tomorrow. Okay, way to go. Go math.